Assalamualaikum and a very good day to everyone. So today we're going to continue on chapter 2, Fundamental of Surface Engineering. So before we proceed to the fundamental of surface engineering, we have to have some basic understanding what are the differences between the bulk and the thin films. Okay, so by definition, the bulk sample we can classify them as the large scale material with three-dimensional structure, which is 3D. Whereas for thin film, we can classify them with material with one dimension or 2D dimension. So usually it's around nanometer to micrometer scale. In terms of the microstructure, the bulk sample usually have uniform grain structure with fewer grain boundaries, whereas for thin film, it will have amorphous polycrystalline or epitaxial type of thin film. For the deposition mode, for bulk sample, you can have this bulk sample by fabrication using casting, sintering, rolling, etc. Whereas for thin film, they have a lot of deposition techniques such as PVD, CVD, sol gel, etc. And also, you have to bear in mind that bulk materials are usually sintered from powdered source materials. The particle size of this powder is in order of 1 micron in diameter, whereas for thin film, it is synthesized from ultrafine particles which is using atoms or cluster of atoms. These ultra-uniform compound materials are possible by synthesizing this in the atomic collision between the atoms and substrate surface. So these are the examples of 1D and 2D structures. So island and dot, we call it as 0D, line of wire is 2D, and film and layer is called as 2D structures. Based on this, you can classify them into unconfined structures, partially confined structures, and fully confined structures. Here we're going to have some definitions and also some differentiation between dimension, example, and quantum confinement of this materials characterization. Before we proceed, we have to understand what is quantum confinement. So quantum confinement refers to the phenomenon where the electronic properties of a material change when the size of the material becomes comparable to the wavelength of electrons. This typically occurs when at least one dimension of material is reduced to the nanoscale level, which is around 1 to 100 nanometer, causing the motion of electrons to be restricted in the dimension. So the next question would be, why does quantum confinement occur? So in bulk materials, what happens is that electrons will move freely within the conduction band. However, when the material size is reduced, which is the thin film structure, electrons will experience confinement, which means that it's been a confined space, which leads to discrete energy level instead of continuous band, which whereas it is similar to the energy levels in the atoms. So based on this understanding of confinement space, you understand that 0D, example as dots, like the previous lecture, and the application is on LEDs, solar cells, and bioimaging. So the confinement is in all directions. Whereas for 1D is nanowires, the confinement will be in two directions. 2D, the confinement will be in one direction, and 3D, no confinement at all. So these are the examples in terms of the OD and also 3D, which is in the isotropic nanomaterial and anisotropic nanomaterials. So what are the benefits of these thin films? So the first benefit is that it increases corrosion resistance. How does this possible? It's because some of the thin film is possible for us to develop a passivation layer and also oxidation layer. So these oxide layers will prevent the corrosive environment from penetrating inside the thin film. The second one is improved hardness. In previous slide, I mentioned that the grain boundaries of bulk sample and thin films are different from each other. The grain boundaries for bulk sample is much more larger compared to the thin film. So small grain boundaries means that it can hinder dislocation, thus increase the hardness. The third one is enhanced magnetic separation induction, increase critical temperature, and also amplify optical observation. So based on the understanding, That is the reason why the thin film technology can be used in all these kind of technology, from display monitors to bionic eyes. Each one of these uses the thin film technology application. So now let's just have some basic understanding of the thin film. So thin film are thin materials ranging from fraction of nanometer to several micron in thickness. It is usually in low dimensional materials. It is created by condensing species of matter by either one by one in terms of atomic, molecular, or ionic deposition. So based on this picture over here, you can see the evaporated atom, the substrate, removal atom, and trap atom. So this is the substrate that you are looking for, that you want to deposit your film onto it. Okay. So based on on this model, you can see that the thin film starts by random nucleation process followed by nucleation and growth stages. The nucleation and growth stages are dependent upon various deposition conditions such as growth temperature, growth rate, substrate surface chemistry, etc. The nucleation stage can be modified by external agencies such as electron or ion bombardment. Film microstructure associated with defect structure and film stress depend on the deposition condition of this nuclear stage. Crystal phase and crystal orientation of this thin film are governed by the deposition techniques. So what does it say here is that when you have this deposition, the most important part is that understanding the parameters of this disposition, because different growth temperature, for example, one material will use 100 degrees C, another material will use room temperature. So the crystalline structure and also the microstructure will be different. The growth rate also will be different, and this will influence your thin film quality. So this is what I have previously stated before in the previous slide, that the thin film grow as in following features, which is you have to understand about the growth temperature, surface chemistry, and then the bombardment of the electron. The basic properties of these thin films, such as film chemical composition, structural properties, and thickness, are controlled solely on the deposition conditions. Thin film exhibit unique properties that cannot be observed in bulk materials because it is result from the atomic growth process on the growing of the substrate. It also that because of the quantum size effect characterized by the thickness, crystal orientation, and multi-layer aspect makes this thin film very interesting. So now we go deeper on the types of thin film that we have. So we have epitaxial, polycrystalline, amorphous, and nanocrystalline. Okay, let's look at epitaxial. Epitaxial thin film can be divided into four. We have homoepitaxy, which is the thin film and substrate that are from the same material. Heteroepitaxy, the thin film and substrate are different material. Pseudo-homoepitaxy, thin film substrate are the same material, but there is a dopant effect which is different from the substrate. And pseudo-heteroepitaxy, which is the chemical commonality between film and substrate. So based on this graph, you can see that the substrate and the thin film are the same grain boundaries, meaning that it is from the same material. So this is called homoepitaxy. Whereas for this one, you can see the substrate and also the thin film are different grain boundaries. So we can classify them as heteroepitaxy. Whereas for pseudoepitaxy, what happens is that, let me just draw here. Pseudo-homoepitaxy is that this is your film, this is your film, this is your film, substrate, and then you have some dopant. Okay, some impurities or some other foreign material that you put on here. So that is called pseudoepitaxy. The next one is polycrystalline. So what happened with polycrystalline? So polycrystalline can be divided into four, which are the textured, grains as with preferred crystal orientation, random. Grain in the films are randomly oriented with no preferred crystallographic. Columnar. Grains grow in a column-like structure perpendicular to the substrate. And nanograin, which polycrystalline thin film with an ultra small grain size, typically less than 100 nanometer. So you can see this polycrystalline, you have a lot of like grains that you can't really determine the structure because it's a mixture of everything. And then from here, you can see that single crystalline means that there's only one type of size. Whereas polycrystalline, it is a multiple sizes of grain boundaries. Whereas biaxial textured film is actually two types of crystal structure. In amorphous, we have four, which is covalent, formed by strong covalent. Metallic consists of metal in disordered atomic arrangement. Oxide consists of metal oxide and polymer materials in disordered arrangement. So based on this, you can see that we have three types of modes of growing thin films. Okay, regardless of the type of thin film, you can use these three modes. So the first one is layer by layer, and then the second one is island, and the third one is the combination of island and layer by layer. So based on this, you can see all these areas over here. So you can see this as amorphous structure. How? Because if it's not amorphous structure, you can see some grains here. Okay, here you cannot see grains, right? So that's why it's called amorphous. Alright, the last one is nanocrystalline, where it is developed by fully dense, which is composedly closed packed nanocrystal with minimal porosity. And then the second type is porous nanocrystalline, contains nanocrystalline grains but with porosity at nanoscale level. Composite nanocrystalline, where the nanocrystalline grains exhibit a preferred crystallographic alignment, and amorphous, which is a mixture of amorphous and nanocrystalline region. So nanocrystalline is usually you can obtain this with soul gel method because it's very tiny crystal structure that is condensed together, agglomerate together. That's why you can see this. So based on that, you have to understand the four terms that we are going to use throughout this surface engineering subject. Okay, the first one is an atom. What is an atom? It is an atom intended to be absorbed and incorporated on the surface. Piezoabsorption is the absorption of the arriving atoms on the deposition surface through weak van der Waals forces. Surface diffusion is diffusion of the physi-absorbed species on the surface before they get incorporated into the film. And last one is chemiabsorption, where direction of the physi-absorption species with each other and then the surface to form the bonds of the film material. Okay, these are the understanding. So based on this diagram, we can conclude that what happened in the first stage when we talk about thin film. So the first stage, what happened is that the incoming vaporized target, so this is the target that going to be vaporize the atom on the substrate or the molecule to the substrate. The stage 2 is the formation of layer by layer atom on the molecule, and the third stage is the growth of the layer atoms of the molecule. Alright, class. Before we proceed to the next one, we have to understand about how does this thin film start to grow. So, in order for us to understand that, let me just give you some analogy or some ideas of how that is occur in our everyday life. Okay, so imagine you are trying to build a small sandcastle on the beach. If you grab just a little bit of a little bit of sand, what happens is that you want to make a tiny tower, right? It will fall apart. But if you keep adding more sand, eventually the pile will become stable and holds its shape. So this is the same concept that we apply when we deposit atoms onto a surface to form a thin film. In a materials engineering point of view, we call this process the process where we put all this sand together to make it stable. We call this as nucleation. And the key theories of this explanation is called the capillarity theory of nucleation, CTN. So what is nucleation? When atoms or molecules start to group together on a surface, they form a very tiny clusters. These clusters, we call it as nuclei. If a nucleus is too small, it will become unstable. Thus, it will break apart like a tiny sand pile that collapses with the sand before. But if the nucleus reaches a critical size, it becomes stable. When it becomes stable, it is possible for the nucleus to keep on growing to become a high quality thin film. So, when we talk about homogeneity of nucleation, we have to understand what does happen when the nuclei grow while other nucleation disappear. So, the growth of nuclei depends on two competing energies. The first one is surface energies, and the second one is volume-free energy. What is surface energy? Surface energy is the energy at the boundary between the nucleus and the surrounding environment. If the surface energy is too high, the nucleus wants to shrink and disappear. Whereas volume-free energy is the energy you gain when atoms come together to form a solid. If the energy is large enough, the nucleus atom becomes stable and grow. For nucleus to survive and grow into thin film, we want higher energy gain and lower surface tension, because if higher than surface tension, the nucleus will shrink and disappear. The next one is that we want to make this thin film, right? So now we know about the critical site. Previously, we know about the surface energy and also how does it react. Now we want to make sure that once when the nucleus can continue to grow, how can we make it stable? So based on this, it will involve some formulation. So there is a certain critical size that nucleus must be stable. If nucleus is smaller than this size, it will dissolve back into atoms. We don't want that. That's why in system production of thin film, we want a larger critical size so that this thin film will continue to grow. This will involve this will involve formulation based on the critical radius, surface energy, and free energy change per unit value. In conclusion, we can say that if the nucleus is too small, it will disappear. And if the nucleus crosses the critical size, it keeps growing from a thin film. So these are the explanation. Okay, you can see here, when the enthalpy G is an energy barrier to the nucleus process, if radius is smaller, the nucleus is unstable. If radius is greater than R, which is the critical size, the nucleus is stable and grow larger thin film. So this is the explanation. Alright, so we have 5 stages of fundamental process. How does this thin film grow? Okay, the first one is that the gas phase atoms are impinging on the surface with the rate of R, where they are absorbed or directly reflected. So this is a thin film. This is a substrate. The gas atom will move the atom to fill in the substrate. The second stage is that on the surface, they can diffuse at a certain distance and dissolve again. This is called re-evaporation. The third stage is that the time of absorption and the diffusion distance depend on the activation energies of desorption and diffusion. For very small impingement rates, an equilibrium between absorption and desorption can be established. It can be categorized by such a low coverage that no nucleation of film will be formed or take place. At high supersaturations, the critical nuclei are very small and can be formed between 2 or 3 atoms. So the fourth stage is that the continuous growth of the nuclei finally will result in nuclear contact of the nuclei coalescence at a continuous film. And the last stage is at high impingement rates, metastable clusters are formed which can be binding or diffusing atom by the impingement of their atoms. So these are the understanding of how this occur. You have to understand about the absorption of the substrate, and then the substrate then will have some energy given away to the top layer to be deposited to the atoms, and then it will occur the binding energy between these two layers. Okay, so in a nutshell, we can say there are 3 steps. The first one is the separation particle from the source, which means from the target, and then the target will vaporize some atoms or bombard some atoms, and then this atom mobility is called as an atom. So this atom will be transported on the substrate where the condensation and also growth of thin film will occur. So step in film formation, first is thermal accommodation, which is the deposition parameters. So meaning that some thermal activities will influence the type of quality of the thin film. Like I said before, some thin film will be grow under 100 degrees C, some will grow under RT room temperature. So these two will give a different crystal structure and also crystal quality. And then what happens is that once thermal accumulation has been succeeded, the atoms will be bombarded and then they will have some binding which have involved physical absorption and chemical absorption, where these atoms will then go to the substrate where these will have some surface diffusion. And then diffusion will occur, some island growth, coalescence between these atoms, and then the next one is the continuous growth of the thin film. So based on that, we have some basic understanding of what is happening. So these are the atoms. These are the substrate. Let's just imagine these are the substrate. Okay. So what happened is that this is the deposition, the atom, right? And then you have the diffusion of the terraces. The next atom will be coming here. So we have a target over here. This is a big target, a metal target to be deposited on the substrate. And then you have another atom, coalescence with each one of them. Alright. This is called the nucleation of the island. Okay. And then the nucleation of the second layer of island. And then nucleation of the lower terrace. So it will go one by one. It will go to the lower energy to fill up whatever they can fill up. And then attachment to an island. And then diffusion along a step edge. And last one is detachment of the island. So that is how the thin film can occur in a process. It takes about like few steps in order for them to make another layer on top of this. Okay. So based on the understanding, we have three thin film growth mode. The first one is island, or we call it as BW growth mode, where the atoms in the film are more strongly bonded to each other than to the substrate. The second type is the layer FBM growth mode, where the atoms are more strongly bound to the substrate than to each other. It's called the layer-to-layer growth. And the last one is the combination between the layer and the island. It's called the SK growth mode. This is a combination between the layer and island, where the example that we want smaller lattice mismatch or suitable for any type of semiconductor. So this is how the nucleation of growth will occur. I will explain this further in our next class. Okay? Our next class I'll explain that. So the formation of stages of thin film, this you have to remember. The first one is the nucleation during which small nuclei are formed that are statically distributed over the substrate surface, and then the growth of nuclei and formation of larger island which often have the shape of a small crystal. And then the third one is that the coalescence of the island and formation of the thin film or less connected containing empty channel. And the last one is the fillings of the channel. So these are the stages in formation of the thin film. So I think for this one, that's all for now. So I'll give you some quiz to answer and then you can fill in your attendance form. So I'll see you in the next class. Thank you so much. Selamat Hari Raya and Assalamualaikum.